The first speaker today is Dr. Fiona Smith, Bureau of Meteorology, Australia. And she is an international leader in using satellite observations to improve weather forecasting with over 20 years operational weather forecasting experience. And Dr. Smith served for a very long time with the UK Met Office, and I understand it recently moved to the Bureau of Meteorology, Australia. So Dr. Smith's expertise is on data assimilation, numerical weather prediction, radiative transfer, hyperspectral sounding, satellite sounding, reconstructed radiances, optimum estimates, and principal component analysis. So today, Dr. Smith will be speaking on using satellite observations in data assimilation. So I welcome Dr. Smith, and we can start. Let me at the outset thank you for agreeing to this request from the organizers. And on the behalf of the organizers and from my personal capacity, I thank you for your kindness in agreeing to this lecture. I'm sure that all the participants would get the benefit of your enlightening lecture. Yeah, please go ahead. Thank you.
Thank you so much. Just checking you can hear me again.
Yeah, we are able to hear you. Yes.
Great. Thank you so much. So it's a real honor for me to have been asked to give this presentation all the way from Australia. So thank you so much for the invitation. As that was a lovely introduction you gave to me. A little bit more about me. As you just said, I work at the Bureau of Meteorology in Australia, and I'm the team leader of the satellite data assimilation team. And I've been here for nearly 7 years now. And before that, I worked at the UK Met Office for about 15 years. So I've worked this whole time in satellite data assimilation. I have two other roles. I'm the chair of the WMO's expert team on space systems and utilization. And what that group does is we coordinate user requirements for satellite data from WMO member states, and we work with data providers to try to ensure that these needs can be met. We also carry out user readiness activities to ensure that our member states can benefit from the satellite observations to generate warnings, situational awareness, and forecasts. I'm also the co-chair of the International ATOVS working group, and this is a sounding science working group under the Coordination Group for Meteorological Satellites and the International Radiation Commission. So one of the main purposes of this group is to provide a forum for exchange of science around the use of sounder data. We also work to establish high-level priorities for meteorological satellite data providers, and we report to the IRC on matters that affect sounding data. So in this talk, it's not really long enough to really do this subject justice, but my aim is to introduce the most widely used of the different types of satellite observations in numerical weather prediction and explain why we use them, to briefly explain the measurement concepts of these types of satellite data, and to provide an introduction to the forward modelling required and the quality control and error characteristics of these observations. So I'm not sure how many of you in the audience know anything about satellite observations, but we use observations from a wide variety of satellites. And in meteorological remote sensing, there are two main types of orbit that we use. The first is the geostationary orbit, which is shown in this outer ring here, and that's a long way from the Earth. And it's positioned so that the instruments so that the satellites are rotating around the Earth at the same speed as the Earth is rotating, so that the satellite always views the same portion of the Earth. And these provide excellent imagery over the tropics and mid-latitudes. We also have polar orbiting satellites, which are shown in the smaller blue orbits here. And these rotate around the Earth much faster at a much lower height. And they will typically pass over the equator at the same local time. So although they move around the world faster than the Earth rotates, that means that the area that they're viewing changes constantly. But every time they cross the equator, it will be, for example, 9 a.m. at that location. There are also some elliptical orbits, which are quite new for us. And I'm not sure that we really use any observations from elliptical orbits in NWP just yet, but I'm sure that will change. Each of those satellites carries a range of instrumentation. And for example, this diagram shows the METOP satellites. They're the European Polar Orbiting Satellites. So they have various instruments that are used for meteorology. And in the ovals, you can see in the red oval, that's IASI, that's the infrared sounder. And in the green oval, there's a suite of instruments that make up the microwave sounder. There's a scatterometer, there's a radio occultation sensor. And then there are some imagery instruments, and this one measures ozone. So during this talk, I will hope to explain to you why we want to use satellite data, and I will then go through the principles of satellite sounding, scatterometers, atmospheric motion vectors, GNSS radio occultation, and ground-based GNSS ZTD. And I know there are a number of oceanographers in the room, and this is really not my field, but I will quickly mention ocean observations for data assimilation at the end. So, why do we want to use satellite data? There's a fundamental difference between conventional observations and satellite observations. Conventional observations such as radiosondes or surface sensors or even aircraft observations are almost always direct measurements. In other words, they measure the temperature or water vapor or wind at the location and the height of the sensor. Satellite observations, on the other hand, are indirect measurements. So they measure a quantity that is sensitive to the temperature, water vapor, or wind in the column of atmosphere or at the surface below the sensor. This makes them a lot more complicated than direct measurements. As well as this, that means that they require more complicated forward models. You can't just interpolate the model column to the location of the observation. You actually have to construct a model equivalent observation from the model data. They can have complicated measurement errors that can be correlated in the vertical or the horizontal. They also can require complicated quality control checks. And finally, they're extremely voluminous data sources, and we have to thin them out. And there are various reasons we have to thin them out. Firstly, just because there's so much data that it can be too time consuming to process it all. We also need to thin them to counteract error correlations that we don't handle well in the simulation system. And we also thin them out to avoid hitting the model too hard with too much information that is in a direction that the model doesn't like. So from all of these, you would think, why do we use these satellite observations? They're really complicated and difficult to use. And whilst that's true, the one thing that they really have is that they have excellent coverage, with each satellite sensing large portions of the globe. And this is particularly important in the Southern Hemisphere, where we have very few conventional observations. The other reason is that they can be sensitive to parameters that it's very difficult to measure in situ. So just to show you the coverage, hopefully some of you will have seen plots like this before, but this shows the observations that are used within a 6-hour global model assimilation cycle. So we have pretty good coverage of surface observations, particularly in Europe and Asia and in Australia. But you can see that in parts of South America and Africa and northern Russia, and Greenland, there are very few surface observations and almost none at all in Antarctica. Coverage over the oceans is still quite sparse. For aircraft data up the top here, there's excellent coverage over the North Atlantic and over North America, but everywhere else in the world, it starts to be a little bit sparse. Radiosonde observations are quite dense over Europe, but really across the whole world, there are very, very few in situ measurements of profiles of temperature and humidity, and pretty much none over the entire ocean. Sondes also report only at twice a day at 0Z and 12Z, but DA cycles run every 6 hours in global models and usually hourly in regional models. So we have a lot of periods of time when we're trying to do data assimilation without many conventional observations. You can contrast this with satellite data. So this shows not even all of the sounders that we use. This shows a selection of the sounder data that we would use in data assimilation. On the right, on the left, you can see ATMS and ATOVs. These are our microwave observations. ATOVs is a collection of instruments, AMSU-A and AMSU-B, or MHS. And the ATOVs together with the ATMS provide almost global coverage every 6 hours and with microwave data. On the bottom right, you can see IASI, which is one of our infrared polar orbiting instruments. There are other infrared instruments, including AHI, which is on the Himawari geostationary satellite. So we have a number of these different instruments. I haven't shown you all of them. And so between them, we get global coverage of profiles from the sounder data every 6 hours. We have nearly global coverage of winds as well. On the left, scatterometers. These give us surface winds, and on the right, atmospheric motion vectors, which give us upper air winds. So these two sources of information are quite complementary. Again, we have nearly global coverage of these. We then have the GNSS observations on the left, the radio occultation, and on the right, the ground-based zenith total delay. The radio occultation has almost global coverage, but a little bit sparse, but I'll come back to the principles of the GNSS data later. The observations are limb measurements, so we actually do scan most of the atmosphere every 6 hours with GNSS. The ground-based GNSS is very dense over Europe, but there is coverage from quite a few other countries as well. So you will have learned in the last week about the data assimilation, the variational analysis, and the cost function that we use to find the most likely state of the true atmosphere. So the top equation shows you the cost function, and the bottom equation is the gradient that we're hoping to minimize. And in this talk, we're not interested in the background profile or the background error. We're only concerned with the part on the right, which is the observations that we feed into this system. So in red, you can see where the satellite observations occur in the equations. And then in blue are the forward model calculations, and green is the Jacobian or the gradient of the forward model. And then in this kind of pale gold color, I hope you can see that, I've marked out where the observation errors are. So I'm going to tell you a little bit about each of these things: the observations, the observation operator and its gradient, and the observation errors. So we need to know all of these things quite well to be able to extract the information from the observations via variational assimilation, or indeed any ensemble DA method. The first observation type I'm going to talk to you about is satellite sounding. So what is sounding? So sounding means profiling. And so what we need are vertical profiles of temperature and humidity. And these are needed for weather forecasting, obviously, because our numerical weather predictions models are fundamentally reliant on temperature and humidity observations being available to keep them on track. Traditionally, these measurements are provided by radiosondes, but since the 1970s, we've had satellite instruments that can do this job as well. The difference is, as I mentioned before, the satellite observations are not direct measurements, and they are not able to be as detailed as radiosonde or dropsonde profiles, but they do have global coverage. In the past, we used to do a retrieval of temperature and humidity profiles and to assimilate those profiles. In the 1990s, we switched to a more modern assimilation system where we assimilate a brightness temperature measurement, which is basically the direct measurement that the satellite will make. How this works is that we have atmospheric emission. So the sounders use emitted radiation to tell us about the atmosphere. And as I mentioned, the measurements are the top of atmosphere radiance or brightness temperature at different frequencies. So a layer of atmosphere, like any other object, emits radiation over a range of frequencies that depend on its temperature and chemical composition. The amount of emitted radiation is determined by the Planck function and the absorption and emission properties of the chemical species that are in the atmosphere and the temperature that they're at. So this shows you the Planck function for the sun in red and for the Earth in blue. So we're trying to sense the Earth's atmosphere. We use two main regions of the electromagnetic spectrum for satellite sounding, the microwave and the mid-infrared. And you can see that the responses of the sun and the Earth are pretty linear in the microwave and are fairly constant relative to each other. Whereas in the infrared, there's a difference between how the sun is behaving, it's quite linear, and how the Earth's radiation profile is, where it's going round this curve. So this gives microwave and infrared sounders different benefits and drawbacks due to the difference in the behavior of the Planck function at those frequencies. So a sounder has a number of channels, and each channel provides a different measurement of brightness temperature. The brightness temperature is calculated from photon counts that are received by a direct detector array. The detectors will be sensitive to particular ranges of frequencies of radiation, and when the satellite receives the signal from the Earth, the incoming radiation is split into different frequencies and sent to the different detectors. Depending on the type of instrument, there can be a lot of ground segment processing to deliver calibrated brightness temperatures to the assimilation system. So for temperature sounding, we're trying to infer the temperature of the atmosphere from the measurement of emitted radiation. To do this, you can use absorption lines of a well-mixed gas. So if you know the amount of the gas, you can work out the temperature that it's at. For microwave frequencies, we use oxygen lines for this, and for infrared, we use CO2. For humidity sounding, it's almost the opposite problem. If you know the temperature of the atmosphere, you can work out how much water vapor is present. So obviously we use water vapor absorption lines to do this. So it's very common to use temperature sounding channels at the same time as water vapor sounding channels, because your NWP background profile probably is not good enough to know the temperature well enough to get the humidity data used properly. So you try to use the temperature sounding channels at the same time to find an optimal fit to all of the channels at the same time. So there's a complication with this atmospheric absorption and emission, but it's a useful one. So Kirchhoff's law says that emissivity is equal to absorptivity. So these emitting layers of gas in the atmosphere will also absorb radiation as well as emit it. So that means that if you have a layer of gas that's emitting radiation upwards towards the satellite, this radiation will be absorbed by the other layers of gas above it. Now, that sounds annoying, but it's actually useful because it means that for a given frequency, the signal that you measure is not sensitive to the whole atmospheric column, but just a layer of it. And I'll show you why on the next slide. So when you're looking at emission from the atmosphere, if you have a layer of atmosphere down towards the surface, you have many molecules. The density of the atmosphere is quite high. So these many molecules are emitting a lot of radiation. That radiation is absorbed by the atmosphere above it. And there's a lot of atmosphere above the lower levels of the surface. So a lot of that radiation is absorbed. On the other hand, if you're in the stratosphere, there are very few molecules. So you don't have much emission. But you're at the top, so there's not much absorption above the layer either. However, in the middle of the atmosphere, you still have quite a lot of emission, but you don't have so much atmosphere above you. So the signal can reach the satellite. This results in a profile contribution here, where your signal is mostly coming from a particular layer of the troposphere. What does this mean for our inverse problem for determining the temperature at a particular height in the atmosphere, which is what we need to do with our data assimilation? So we have one radiance measurement that has differential contributions from across the full atmospheric profile. So how do we get the temperature from this one measurement? The answer is that the amount of emission at a given frequency depends on the location of specific absorption lines for your chosen absorbing gas. So if your frequency is very close to the center of an absorption line, then the few molecules high in the atmosphere generate a very strong emission signal. And emission from molecules in the lower part of the atmosphere will mostly be absorbed by the molecules higher up. The atmosphere is very nearly opaque. But if you move further away from the center of the absorption line, then the few molecules high in the atmosphere no longer dominate emission, and emission from the lower parts of the atmosphere will reach the satellite because it's more transmissive. So if you use a set of channels at different frequencies, you can produce a sounding of the atmosphere. So if you know where in the atmosphere the signal is coming from, you can work out the temperature of that layer of atmosphere, and the different channels are chosen to be sensitive to different parts of the atmosphere. So that's talking about the emission. There are other things that we need to worry about. That's emission from the atmosphere. We also need to worry about the surface emission. At certain frequencies, the signal from the surface can also reach the satellite. Now, the other fundamental bit of physics we need to remember is that emission is 1 minus the reflection. So we also have downwelling radiation that is reflected from the surface and bounces back up to the satellite. So we've got actually 3 terms in our forward model, the radiative transfer equation. So if we are close to an absorption line, we can ignore the surface emission and reflection as the absorption is going to dominate. Oops. So we're left just with this central term that describes the upwelling atmospheric emission. So you'll notice that this is an integral from the surface to space of the brightness temperature resulting from the particular temperature of a layer of gas times the upwards weighting function. And this weighting function is basically the change in transmittance with respect to height. So this determines how much your emission is absorbed by the atmospheric layers above us. For well-mixed gases such as carbon dioxide and oxygen, if you're fairly close to an absorption line, this weighting function is a function of height. And if you're near a water vapor absorption line, it's a function of the water vapor burden, the amount of water vapor at that height. So I'm going to tell you a little bit more about how we can get our heads around the weighting function in the next slide. So if you're far away from any absorption lines, the atmosphere is transparent. There's nothing to absorb. There's no gas that will be absorbing the radiation because the gas is not sensitive to that frequency. So in this case, you would say that the atmosphere is transparent. Your transmittance profile goes immediately to 1 at the surface. The weighting function is the differential of the transmittance. So it will look something like this. It will very rapidly, in reality, it's not quite a delta function. So it will go to 0 very quickly in height. So this channel would be sensitive to surface emission. If you're at the top of the atmosphere is opaque. So your transmission is 0, your transmittance is 0 all the way to the top of the atmosphere, and then suddenly it shoots up to 1. So your weighting function in this case will look like a curve that's very sharply peaked at the top of the atmosphere. So this channel would be sensitive to stratospheric temperature. For a normal sounding channel, the atmosphere is transparent at the top of the atmosphere and then gradually becomes less and less transparent as you get a greater mass of atmosphere. And then down towards the surface, the atmosphere is opaque. So the differential of this function looks something like this dashed curve, which is a peak, is a curve that peaks at a particular height. And that peak determines where the sensitivity of this channel mostly is. So depending on what frequency you use, and that will change the transmittance, and the peak will move up or down. So what we do for a sounding instrument is we use a set of channels measuring at different frequencies to get a set of measurements that are sensitive to different ranges of the atmosphere. Now, I said earlier that satellite soundings are not as detailed as radiosonde or dropsonde profiles. It's a common mistake to think that satellite soundings can replace radiosonde profiles, but they will never be able to do so. So if you look here at this chart, what we have plotted is in black, this is some dropsonde profiles, and in colored lines, you can see various different retrievals from different profiles, different first guesses of this same scene. And you can see that the dropsonde has a very, very sharp change in this is water vapor that we're looking at, in the amount of water vapor in the boundary layer. It jumps immediately up from like 4 to 15 over a very, very sharp range. And the sounding just cannot capture that vertical detail. The vertical resolution of the retrieval is determined by the averaging kernels, which is calculated from the background error, the observation error, and the Jacobian. And none of these things have very sharp features. So it's impossible for a satellite sounding to resolve these very sharp features. So I mentioned before there are 2 types of sounding instruments. I will tell you a little bit more about both of those. So in the microwave spectrum, as I mentioned, we use oxygen absorption bands for temperature sounding. So the main oxygen absorption band that we use is between 57 and 60 gigahertz, where there's a complex series of absorption line. There's also an atmospheric window where the measurement is sensitive to the surface properties, and this can help us with using the lower atmospheric sounding channels, which do see a little bit of the surface. And then at 183 gigahertz, we have a set of water vapor sensitive channels. So this shows you the weighting functions of the temperature sounding channels on AMSU-A. So you can see that we have a set of 15 channels which span the full a large proportion of the atmospheric column. This is a log pressure chart which goes up to 1 millibar. So you can see that we have channels that peak quite evenly spaced through the atmosphere. So what are the main benefits of microwave sounders? As I mentioned, we're primarily interested in temperature and water vapor information from these instruments. And the reason that we like microwave sounders is that the effects of cloud in the field of view can generally be neglected, because at these frequencies, scattering and emission from clouds is negligible. This means that we have really good data coverage in meteorologically active areas. In other words, areas where there's real weather, where there are clouds present. Another advantage is that the channels are not affected by trace gas emission, and the channel measurements are reasonably independent of each other. They don't tend to have instrument error correlations. The real advantage nowadays is that in modern DA systems, we can use microwave channels to retrieve not just temperature and water vapor, but also cloud liquid water and ice water content too. This means that in advanced DA systems, all sky use of microwave data means that the microwave radiance observations give the most impact of any kind of observation in these NWP systems. Another advantage is that they have sharper weighting functions than infrared instruments. So in contrast, this shows you the infrared spectrum. This is in wave numbers from 600 to 3000 wave numbers. And this is the typical range that's spanned by your infrared sounders, such as ERZ and CRIS. There are a lot of features in this graph relative to the microwave spectrum that I showed you earlier. Each one of these little lines is an absorption line of some gas or other. We have two main carbon dioxide absorption bands, one at around 700 wave numbers and one at 2300 wave numbers. And these are used for temperature sounding. We tend to mostly use this one here at 700 wave numbers because the short wave channels are affected by solar reflection at certain times of day. So it's easier for us to use these ones. There are also atmospheric windows where the atmosphere is transmittive. And at those frequencies, we can see down to the surface. And that, again, to have some channels which are sensitive to the surface helps us with cloud detection. And it also helps us to use channels that are slightly sensitive to the surface. This broad U-shaped feature that we can see here in the middle is the water vapor absorption band, where there are many, many water vapor features. Some of these lines have stronger absorption than others. So, you know, over here, the absorption is not as strong as it is over here. And that is how we can do the sounding. The weaker lines allow us to measure emission from lower parts of the atmosphere, while the stronger absorption bands allow us to sense at the top of the troposphere and into the stratosphere. So the other feature of the infrared spectrum is that there are absorption lines from all sorts of gases. And here we've got a few marked from dinitrogen oxide, carbon monoxide, methane. There are a lot of spectral features in this part of the spectrum, which can be a little bit confusing and does mean that makes for some complications in using infrared data. This shows you the Jacobians against from ERZ against the AMSU-A weighting functions. So the plot on the right is the same one that I showed you before. It's just squished down to match the height on the plots on the left. So in fact, we've got weighting functions in the very left-hand plot and Jacobians in the middle plot. And I'll come back to that a bit later. But broadly speaking, they're, for this purpose, roughly the same thing. So on the left, you can see there's an awful lot of lines here. So this instrument ERZ has 8,461 channels. So we don't use all of those. We only use about 150 of them. And those are plotted in the middle. So this is 150 of these versus 15 of those. And you can see that they're not quite as nice and simple and evenly spaced as the ANZUA, but because we have so many channels, we can actually get a higher vertical resolution. So you're probably wondering what the main drawback of the infrared is, and the answer is quite straightforwardly cloud. So this image shows a window channel of the AHI radiometer on the Himawari satellite, and you can quite clearly see these blue and green features are cloud. So if you've got a cloud in the field of view, you're not able to see down to the surface of the Earth. You can only sense down as far as the cloud. So why do we want to use the infrared sounders? So again, they're fundamentally sensitive to temperature and water vapor, which is good. And so the modern hyperspectral sounders, these ones with the thousands and thousands of channels, as I mentioned, give us higher vertical resolution than the microwave. So if you were to have a clear sky scene, the information content for NWP is about 4 times higher from the infrared than from the microwave instrument. Conversely, if you have a sounder on a geo platform, all of the sounders on all geo platforms are infrared, because microwave instruments would require an absolutely enormous antenna, and nobody yet has been able to build an instrument that would work on a geostationary platform in microwave frequencies. So if you've got a sounder on a geo, it's an infrared one, and that's really advantageous because they provide very high temporal resolution. The IR sounders tend to have much smaller footprints, around 12 kilometers versus around 50 kilometers for microwave, so they also have higher spatial resolution. Modern DA systems can assimilate the information about where the top of the cloud is, and some DA systems use ozone-sensitive channels to extract information on ozone. So how do we get the information from these sounder observations? We'll go back to the cost function and its gradient. And now what we have is brightness temperature observations in red, and in green and blue, we have this, the forward model and the gradient come from a radiative transfer model. So there are 2 main fast radiative transfer models used in DA, RTTOV or CRTM, and NCM RWF and the Bureau of Meteorology and most European centers use RTTOV, whereas the American centers tend to use CRTM. So I've been talking about weighting functions and Jacobians, and I think it's worth just explaining the difference. So the weighting function, as I mentioned previously, is the differential of the layer-to-space transmittance with height. The Jacobian is the gradient of the radiative transfer equation. So it represents a change in the radiance with a unit change in a specific quantity in the atmosphere. So for temperature sounding channels, the Jacobian and the weighting function are actually almost the same. They look very similar. I would challenge somebody to easily spot whether somebody's plotted a weighting function or a Jacobian. For water vapor sounding, though, the channels are sensitive to both temperature and water vapor. So whilst there can only be one weighting function, it's the differential of the transmittance, there are 2 Jacobians. There's a temperature Jacobian and a water vapor Jacobian. In particular with water vapor, they can also go negative. So a positive change in the amount of water vapor can sometimes cause an increase in the brightness temperature, sometimes a decrease in the brightness temperature. In any case, the Jacobian is the quantity that we need during data assimilation. So what processing steps do we have to go through to use these observations? The first one I'm going to mention is for the infrared, we need to remove redundancy from this 8,000 channels. So we do what's known as channel selection. And in fact, we do channel selection for every sounding instrument, even the microwave ones. We don't always use all of the channels. This could be because some channels are affected by cloud or other things that we don't, or rain or something that we don't like in our retrieval system. But in the infrared, we have an extra problem because we have 8,461 channels on EASI, but the information content studies show that we've only got a few tens of pieces of information. In other words, there's much redundancy, and a lot of these measurements are highly correlated and have highly correlated errors. The radiative transfer is expensive, and we can't simulate every channel. It's just too time consuming for these real-time systems. Some of these channels are also sensitive to trace gases, and we don't know how much methane or carbon monoxide there is at any given location in space from a numerical weather prediction model. So we just can't use channels that would be sensitive to those quantities. Subselecting channels also helps us to reduce error correlations. Correlated errors between channels can complicate our use of observations in data assimilation. After we've done this channel selection, what else do we need to do? We need to do quality control. All sounding instruments have biases that need to be removed. These biases could be due to variations in the reflectivity of a black body source on board the satellite. They could be due to some reflected radiation getting into the sensor. They all have different characteristics, and they all have biases that need to be removed. Both microwave and infrared observations may also be sensitive to geophysical features that are not well represented by the model. For example, this could be skin temperature or surface emissivity. And particularly if you have a regional model where the model top is around 40 kilometers, you're also sensitive to the temperature above the model top. The top of atmosphere measurement is well above 40 kilometers. So what do you do when your model top is 40? You have to do something to extrapolate the profile above that. Or you have to remove channels that are sensitive above 40 kilometers as well. As I mentioned, infrared observations are strongly affected by cloud, and microwave observations can be sensitive to rain in the field of view, and some of the channels are a little bit sensitive to cloud. So screening is necessary in some cases, and pre-processing is often required. I'll talk about bias correction in a little bit more detail. On the left here, you can see a bias-corrected METOP-B ERZ channel. On the right is the bias correction that was applied to the raw data. You can see that there's something fundamental that we're removing here, and that's a scan bias. So you can see that this bias correction is greater at the edges of the scans than in the middle. But you can also see some actual genuine physical features. You can see quite clearly around Greenland and around the edge of South America that you can see a difference between the bias correction applied over land and over sea, and here also over sea ice. Bias correction schemes differ, and so we can use different types of predictors to work out what the instrument bias is. Your fundamental aim is to remove only the instrument bias, but because we need to use model information to carry out this bias correction, you can sometimes end up removing model biases as well. And sometimes this is maybe warranted because it affects the radiative transfer process. And so you need to remove biases that result from errors in the radiative transfer as well. So in this case, this particular bias correction scheme uses skin temperature as one of the predictors. And that's why you can see a difference over different surface types. So I mentioned previously that observation error was something that is really important to data assimilation systems and to our correct use of satellite data. Traditionally, for sounders, you have a set of channels and the observation error covariance matrix is diagonal. It would comprise excuse me, components that we would make a guess as to what the total error was based on an understanding of instrument noise, which we normally know very well, and that's usually provided by the instrument manufacturer. There's also a radiative transfer error, and it's common to assume that that's about 0.2 Kelvin. And then there are any other effects, such as the effect of trace gases that you know are present in the atmosphere that you don't include in your radiative transfer calculation. So typically you would add these errors up for each channel, and then you would inflate this whole thing. You would make those errors bigger by a factor, a fairly arbitrary factor. And the reason that we would do this is to take account of missing correlations between the errors in the different channels. And one of the things that is really correlated between different channels is the fact that the model only measures, for example, on 80 levels in the vertical, whereas the real atmosphere obviously doesn't have levels in it. It's a full continuous effect. So and the model obviously has a specific horizontal resolution, which again is not the case in real life. There's very fine features in the atmosphere that the measurement is sensitive to, but the model cannot measure. And this causes a type of error called a representation error. And these errors can be highly correlated between different channels. So we inflate this matrix to take account of errors such as the representation error, and also horizontal correlations between different observations in different locations. And also just to improve the mathematical stability, because these matrices need to be inverted, and sometimes you can find that the calculations just don't, the minimization just does not work very well if your model becomes mathematically unstable due to very small eigenvectors in these covariance matrices. We found that for hyperspectral sounders, and increasingly for microwave instruments, though, that this simple error representation is not sufficient. So we're now using more complex modelling, and in particular, the use of diagnostic methods such as the de Rosier technique. And this is a method by which you can use observation minus background and observation minus analysis quantities to diagnose the error covariance matrix. Interferometer channels, the infrared instruments like ERZ and CRIS, are correlated anyway because the measurement technique of an interferometer just creates correlations between the different channels. But as I mentioned before, the errors of representation are usually highly correlated, particularly for water vapor channels and for surface sensitive channels. For the microwave, we now use observation errors that are situation dependent. So you would have a different observation error for an observation over sea ice versus over the sea, or if there's cloud in the field of view versus a clear profile. And so using more realistic representations of the observation error means that we can extract more information from the observations. These plots show an example of interchannel observation error correlations for ERZ on the left and CRIS on the right. And these are the observation error correlations that are used operationally at ECMWF. Now, these two matrices are not they're not equivalent. They're not the same sensitivities. They're not the same channels in both of these plots. But you can see some broad features that are in common. So you've got a big square block in both of these sets of channels, and these are the surface sensitive channels. And then further along, you've got areas that are sensitive to the water vapor, and then more surface sensitive channels again. So this would be the water vapor region for ERZ. So you can see that the correlations are stronger in the water vapor and then the surface, whereas the temperature sounding channels are relatively uncorrelated. The correlations are higher, off-diagonal correlations are higher for CRIS than they are for ERZ. These, like I say, these errors are diagnosed. So this is what the system sees. So that concludes what I was going to tell you about satellite sounders. So I'll now move on to other types of observations. And next we're going to talk about scatterometers. So scatterometers, as I mentioned before, give us surface wind information. So these instruments are active instruments. They're radar instruments, so they emit a pulse and then they measure the returned signal. They're normally flown on polar orbiting satellites because radar instruments operate in microwave frequencies. And, the same issue applies here with the size of the antenna that will be needed if you put it on a geostationary satellite. They have the same advantages of microwave radiances that because in the microwave spectrum, clouds are generally transparent. We can see through the clouds, although there are some impacts of rain, depending on the frequency of the scatterometer. So what scatterometers measure is backscatter. They don't measure the wind directly. As I say, satellite observations are never direct measurements. So the backscatter response is sensitive to different things depending on where in the world you are. Over the ocean surface, they're sensitive to surface wind because the surface wind changes the roughness of the surface and that changes the backscatter. They're also over land can be sensitive to soil moisture, which changes the properties of the surface and the amount of absorption of the signal. And over the sea ice, you can find that the signal is correlated with the ice age, because as ice ages, it becomes different, it becomes more rough. So you can kind of see some of these effects in the picture on the left here. So for NWP, we're mostly interested in the use of the data over the ocean to get at the surface winds, but we do also use the observations over land in our land surface data assimilation schemes. So as I mentioned, what's provided to the NWP system is a wind vector. It's not the backscatter. And the ASCAT data can also be provided, as I mentioned, over the land. And in that case, we'd get a soil moisture quantity. So the assimilation system does not need to forward model backscatter in the same way that the sounder assimilation does not forward model photon counts. So there's a lot of pre-processing done by the data provider to convert a backscatter measurement into a wind vector. However, the benefit for us is that the forward calculation is simpler, but the errors can still be complex. A rather unique feature of scatterometer observations is that they provide ambiguous wind vectors. Basically, it's not possible to uniquely determine the wind speed and direction from the backscatter signal, and I'll explain that a bit more on subsequent slides. Quality control is needed with these observations, especially when the measurement uses the KU band. That means that the signal can be affected by rain, so we need to be careful to remove rain-affected observations. So as I mentioned, backscatter is our measurement, and that's also known as sigma naught, and that's the power received over the power transmitted. It's also known as the normalized radar cross-section. So scatterometers view the ocean surface at an angle of approximately 60 degrees, and at these incidence angles, Bragg scattering is a dominant physical process, and that type of scattering means scattering from surface waves where the wavelength is similar to that of the radar beam, which generates a resonance. So for our scatterometer frequencies, that means that waves of around 2 to 6 centimeters in wavelength are going to give us our signal. And so that's quite small. We're not measuring the wave swell at all. We are literally talking about very instantaneous responses of the very surface of the wind to the very surface of the ocean in response to the wind speed. So the other thing to bear in mind is that the wave caps align perpendicular to the wind direction, and this will be important to consider later. So this just demonstrates kind of what happens in each case. So we have an incident ray. This is our signal coming down from the satellite, and that's represented in these diagrams by the thick arrow, the black one or the white one in the case of the lower image. And the signal that is reflected from the surface is shown in red in each of these pictures. So if you have a very, very still sea, it's like a mirror, it's specular reflection. And all of the signal will be directed away from the direction that it came from. So the backscatter will be 0 in the case of a perfectly smooth ocean surface. As the sea starts getting a little bit more rough, you start to get some backscatter, and some of the signal is reflected back in the direction of the satellite. As the sea gets rougher and rougher, the scattering gets greater and more of the signal is returned in the direction of the satellite. At some point you saturate when the wind speed gets really, really high and you can no longer detect changes in the wind speed. So I mentioned before that the backscatter is converted into a wind vector by the data providers, and to do this they use something known as a geophysical model function. So that is basically an empirical function based on a collocation between observations and NWP model winds. And so the sigma naught is a function of the wind speed, the relative wind direction relative to the viewing geometry of the satellite, the incidence angle, the radar polarization, and the radar wavelength. And so basically they perform an inversion where they vary the wind speed and direction to minimize the difference between a model sigma naught and a measured sigma naught. So there are two unknowns. wind speed and wind direction, and we need multiple views of the ocean to unravel that. And I'll again explain a little bit more in the next slides. So the first thing to note is that backscatter has a cosine dependence on wind direction. So you can see this cosine function here. So that function basically, depending at several different angles, could generate the same backscatter. If you think about it, if something aligns north-south and you're looking at it east-west, you can't really tell whether the wind is coming from the north or coming from the south, because everything will still be aligned in the same way. The other thing to note is that the amplitude of this cosine function varies depending on the wind speed. So, for example, if you had a signal at 30 sigma naught, if your sigma naught was minus 30, that could either be a wind in this direction of 15 meters per second or a wind in this direction of 20 meters per second. So there's some ambiguity because you have two unknowns, both the speed and the direction. So this is, as I mentioned before, you need to look at the surface from several different angles in order to be able to unravel this information. So from just one look at the surface, you can't tell whether the wind is coming from the north or from the south. However, if you were to, as well as looking at it from the east or the west, if you were to look at it from the northeast or the southwest, then you would get a different view of those aligned features on the ocean surface. If you have two looks, you can start to generate some solutions. With two looks, you get 4 different solutions. They're equally probable. So this is still not very useful for NWP because you don't know which of these 4 winds is actually the right one. If you look at it 4 times at different angles, though, you start to generate some probability as to whether these two, they'll be 180 degrees apart, but they're more likely than these ones here. So you need to have multiple looks at the surface to find out what the answer is. Even so, we still have ambiguous winds. We have 2 probable solutions. So how do we get around that in NWP? The answer is that we handle these ambiguities in 4D VAR. We basically add an extra part to the cost function that allows any of these wind aliases to influence the analysis, but we weight those wind aliases depending on what we think the probability that they're right or wrong is. So we have a cost function that's a function of the observed and latest atmospheric state during the minimization, and a function of the observation error. So we switch on this extra cost function after 20 iterations in 4D VAR in our system, and then what we need to do is essentially find out what this probability of gross error is, and we'll just basically really downweight the winds if they're not working, if it's too ambiguous and we can't work out whether it's right or wrong. I'll show you an example of this in practice in the next few slides. I'm not sure whether you'll be able to see this clearly on your screen or not, but in red we have the model wind, and then in shades of blue we have the ASCAT wind, where the darker the shade of blue, the more probable the solution. So you can see that in some cases, oops, I skipped a bit. Oh, it's not showing up. That's a pity. In some cases, so down here, for example, the wind is fitting really well. So in this case, it's aligning quite nicely with the observation vector. Up here, we've got some ambiguous winds where, in the case on the left, they're going in a completely different direction from the model. And over here, we've got 4 equally probable directions. So I'm going to show you how that's handled in the assimilation system. So after our first iteration, we update the probabilities. And in most cases, our winds align reasonably well with the model. So we end up with one of our ambiguous winds being given a lot of weight and the other being given almost none. But in these areas, like I mentioned, we've got we've got up the top, we've got this case where the ambiguities are still not fitting well. So we still give higher weight to one of the observations than the other. After 20 iterations, we switch on the VAR QC, and now we find that the observation that agrees poorly with the model is given significantly reduced weight. So that north pointing arrow has gone from being dark blue to being light blue. We don't like any of those winds, basically. And then after our 30th iteration, it's reduced even further. So that's how we use scatterometers. I will now tell you about atmospheric motion vectors. So this is another type of wind observation that we use. And while the scatterometer gives us winds that come from the surface, the atmospheric motion vectors give us upper air winds. So what are AMVs? So they are a wind speed and direction measurement that is derived from pairs of satellite images. So again, because we've derived a wind speed and direction, we've got a simpler forward model than for radiance measurements. But on the flip side, the errors are very complicated, and that's because they depend on a priori information that the wind detection scheme requires to work out where there are clouds and how those clouds evolve. And there can also be the other reason the errors are more complicated is because there can be errors in both speed and direction, or the AMV could be assigned to the wrong height in the atmosphere. And I'll explain more about this in the next slides. So if it's so difficult to get the errors right for these measurements, and they're derived from satellite imagery anyway, why don't we just assimilate the imagery and just get the winds from assimilating the imagery? And in the long run, that might be the way things go. But for the moment, we just actually extract the wind information more efficiently by calculating these AMVs and adding them into the system. I mentioned before that we need to really thin out observational data, and that is particularly true for geostationary radiance data. These satellites produce observations every 10 minutes, and we cannot assimilate all of the observations with very dense spatial coverage every 10 minutes from the radiances. It's just too expensive. So it's much better for us to extract the wind information from them and add that in separately. We would also need to be very good at assimilating clouds, because these wind vectors are mostly derived, or partially, some of them are derived from cloud imagery. So how does it work? What we do is we first of all get our image and we do initial corrections so that we do that navigation, things like that, calibration, so that we know where in space we're looking. We then pick a feature. So we find a box of 24 by 24 pixels. So this is an example from MSG, and that has pixels of about 3 kilometers for most channels. So we use 24 by 24 pixels and we find a feature we want to track. We wait 15 minutes for the next image to come along, and then we do a scan of a box of 80 by 80 pixels centered around our initial box. And we look for that same feature again, and we can see that it's moved. In this case, it's moved up to the northeast. So we do a best match of the individual pixel counts of the target with all possible locations until we find that target. Oops, sorry. So we normally then repeat this process from image 2 to image 3 to give a second vector for quality control. We then assign a height to the derived vector, and that's the bit that's really tricky. So we used to use or the data providers used to be quite reliant on NWP information to determine what height this wind was likely to be at. But nowadays, we tend to use pixel-based cloud schemes developed in the cloud community. So at the same time as generating your AMVs, you'll be generating image products, and some of those image products will be a cloud height. And so you can use those cloud height products to tell you what height the AMVs are likely to be at. So we use two different types of satellite to generate AMVs. Traditionally, they were a geostationary image product. So you frequently view the same area of the Earth's atmosphere with the geostationary satellite. So it's very easy to track features across these successive images. And we've got this, sorry, I've borrowed these slides of somebody else, and there's some strange automatic advancing thing that goes on with them, I'm afraid. So with a constellation of geostationary satellites around the center of the Earth, we have 6 or 7 of these satellites now, geostationary ones around the center of the Earth. I'm afraid I don't have any INSAT observations plotted here or GeoCompSat. Oh, this is really annoying. I'm really sorry. But it's possible to produce AMV data that covers the whole of the tropics and mid-latitudes. Since 2002, we've also been producing AMVs from polar orbiting satellite imagery. So in this case, you would track the movement of a feature between successive overpasses. Now, these overpasses can be successive overpasses of the same satellite, or they can be successive overpasses of, for example, METOP B and METOP C. So these winds are complementary to the geostationary AMVs because these can only be generated over the poles where we have a high degree of overlap in the orbits of the low Earth orbiting satellites. So the main issue that we have with AMVs, as I mentioned, is that they have complicated errors. We start with radiance data, and these have relatively simple errors, but then we add in short period forecast data, radiative transfer models, we do a tracking step, and then a height assignment step. And all of these add complications to our errors. There are also assumptions in the derivation and in the assimilation process as well. We assume that the winds are valid at a point. We also assume that the features we're tracking, that the clouds don't evolve over time, that they just act as passive tracers. And if you ever look up at the sky and look at clouds, you will know that they don't just move, they also evolve, they get bigger and smaller. We also assume with AMVs spatially and temporarily uncorrelated errors, which is also an assumption that we know doesn't hold in real life. So we have to thin them and we have to inflate their errors to account for this. Another issue that we have with AMVs is that different software, different data providers use different software to derive the winds, and they have different characteristics. So each new AMV will need more work doing to it to understand what its error characteristics are. So I mentioned before that there are two independent sources of observation error. There's an error in the vector in the speed and direction, and that is linked to the accuracy of the tracking step. There's then an error in height, which is linked to the accuracy of the height assignment. And this is particularly important if you're in an area of large vertical wind shear. So one way that we try to, it's easiest to sort of explain this by an example. So if your wind is assigned a height which is wrong by 80 or 100 hectopascals, then depending on what height is assigned, that can mean a massive difference in your error in speed and direction. So, for example, if your wind measurement was made at if you have a wind that's at 350 hectopascals, if your measurement was wrong by 80 hectopascals at this height, then the wind speed error would be around 12 meters per second. However, if your observation was wrong by 80 hectopascals and the actual wind height was 600 to 700 hectopascals, you can see that the error in the wind speed would only be around 3 meters per second. So one way that we can deal with this is to combine the height error with the UV error so that we just have one. We basically are downweighting winds in parts of the atmosphere where it's really important that we know what the height is, whereas in parts of the atmosphere where there's less vertical wind shear, it doesn't matter so much if the height assignment is wrong. So we can give the UV winds a lower error. All right, so I will move on now to GNSS observations. So there's two kinds of GNSS observations. There's actually three. So all of these types of GNSS observations require the use of the Global Navigation System satellites, which are in medium Earth orbit. So you will know about these satellites because these are the ones that tell you where you are on the Earth. They send out a radio signal. Now, normally, the time taken to receive that signal is used to determine where you are on the Earth. So, you'll use a triangulation based on receiving a signal from multiple GNSS satellites. But if you know the position that you're at, you can use the time difference to determine the properties of the atmosphere. So there are three types of GNSS observation. The one that has probably been the most famously used in NWP is radio occultation. So that involves putting a sensor not on the ground, but on a low Earth orbit satellite. And that low Earth orbit satellite will track the GNSS satellite as it rises or sets over the horizon. And so it will use the distance between those two satellites, which we know really well, and the time taken for the signal from the GNSS satellite to reach the receiver on the LEO satellite to measure the atmospheric temperature and humidity. On the other hand, we can also use ground-based GNSS. So in this case, the signal that's received at a ground station that we know exactly where it is relative to the satellite, we know what the time difference should be, and we can use the delay in that time to measure the total column water vapor in the lower atmosphere. There's a third type of GNSS observation, reflectometry, and that's only just coming into use now. It's still an area of active research and isn't actively used in NWP. So GNSS observations are also active observations because they rely on a signal that's transmitted from one satellite and received by another. Radio occultation is really probably, along with microwave sounding, the most high impact observation type in NWP. So the reasons why we like these observations is that they are extremely high resolution in the vertical, 100 meters to 1 kilometer. There's also no bias in the measurements because it's a time signal calibrated to atomic clocks. And this is really useful for us because it allows it to be used as an anchor. In particular, it's absolutely vital for successful bias correction of radiance measurements. As we mentioned before, bias correction is a very important step in radiance measurements, and the bias correction relies on model predictors. Now, if you didn't have GNSS-RO, the model could just disappear off, and the bias correction between your satellite and the model could basically reinforce the model bias. And so the model bias will then tend towards the climatology, and your radiance data won't be able to do anything to correct it. With GNSS-RO in the system and other conventional observations that make direct measurements, you can anchor the bias correction to those observations that are unbiased. And you can basically pull the satellite radiances back so that they're aligned with the GNSS-RO, which allows you to correct model bias. GNSS-RO observations are uncorrelated in height, which is, again, very different from sounder data. And because again, they use microwave frequencies, they're insensitive to cloud and usually to precipitation as well. On the downside, radio occultation measurements are a limb measurement, so they measure in the horizontal, so they have very poor horizontal resolution, and they also have little sensitivity to the lower atmosphere. I'll show you these features in the next slide. So on the right, we'll start on the right, and you can see this compares what happens with a delta function input signal shown in the solid black lines. This is how that signal would be received by ERZ and radio occultation. So this is kind of like your Jacobian of that signal for ERZ. It's quite broad, looks like one of those actual ERZ Jacobians. With the radio occultation, it's basically the same width as the input signal itself. So the GNSS-RO can resolve sharp features in the vertical better than ERZ. However, if we move to the figure on the left, the dotted line shows you the background error. And then this dashed dot line is the error in your analysis if you only assimilated ERZ. And you can see that whilst there's information throughout a lot of the atmospheric column, in particular, the error is massively reduced down towards the surface here. So ERZ is giving you a lot of information down at the surface. Conversely, the radio occultation, this is the dashed line is radio occultation, that removes so much error in the upper atmosphere. But then when you get down to the height where ERZ starts being really useful, actually the radio occultation is not so able to remove the errors from the background. So these two instrument sources are really complementary. If you have both of them together, your retrieval error is the solid black line. So that's like a really good combination of instruments. All right, so let's go into how the measurements are made. As your LEO satellite rises or sets behind the limb, the measured signal from the GNSS satellite is bent using, it's basically bent. You work this out using Snell's law, which tells you how much the amount of bending is dependent on the change in refractive index between two layers. So that's really what we're going to use to get at the temperature and humidity, because the refractive index is dependent on the density of that layer. So the two things you have to remember are this amount A, which is called the impact parameter, and that is the height in the atmosphere at which this bending occurs, and alpha, which is the bending angle. So generally, we assume what's known as spherical symmetry. So this is a way that we have to make an assumption, because otherwise an infinite number of bending angles could give us an infinite number of different bending angles could be resulted depending on the differences in refractivity. We have to make an assumption somewhere, and what we do assume is that basically this geometry is the same at the LEO satellite as at the GNSS satellite, which isn't exactly true, but it's the way that we can actually get some information out of these observations. So as this satellite moves, the LEO satellite moves away through the atmosphere, the signal will be bent more, and this point, the tangent point, the point at which it starts to bend back towards the satellite, samples every 100 meters through the atmosphere in around 100 seconds that the two satellites can see each other. So what the observation is to the NWP system is a bending angle, or a profile of bending angles, I should say. And I'm going to tell you how that bending angle is derived from what the satellite actually measures. So the GNSS receiver on the LEO satellite measures phase delays at two different frequencies. So there's a signal sent out by the satellite at two different frequencies. The reason we use two frequencies is because they are differently dependent on ionospheric, on the bending in the ionosphere. So you can remove the ionospheric effects by using two signals. So as I mentioned before, the phase delay is a reference to atomic clocks. We know where the satellites are in space very accurately. So knowing those locations, and that means we can calculate what the phase delay should be if there was a straight line between the two satellites. So we can then calculate the excess phase delay due to the bent beam relative to the straight line difference. A Doppler shift is then calculated at those two frequencies by differentiating the excess phase delay as a function of time. And then that's converted to a series of bending angle profiles as a function of impact parameter, which is approximately height in the atmosphere. So as I mentioned before, an infinite set of bending angles could produce the same Doppler. So what we do is we assume that this impact parameter has the same value on both sides of the tangent point, essentially for both of those satellites. So if I go back to the previous slide, that's equivalent to assuming that AG is the same as AL. So we've got a bending angle signal, and how do we forward model that? So we take our temperature profile and our water vapor profile, and we use this equation to convert that into a refractivity profile. The refractivity is then related to the refractive index. And the refractive index is a function of the bending angle according to the equation on the left, which is known as the Abel transform. So this is our forward model, is the Abel transform, and our gradient comes from the inverse Abel transform. So there are some complications. We have two unknowns. We have the partial pressure of water vapor, and we have temperature. So because we have two unknowns and only one measurement, we need a variational retrieval to try and find the best fit. I've already mentioned the need to assume spherical symmetry. This equation is completely dependent on the assumption of spherical symmetry. The other issue is that in order to do this inverse calculation, we need to extrapolate the bending angle to infinity in order to be able to do this integration. So we have to assume a bending angle climatology above 60 kilometers, and that introduces correlations. So just going back to the expression for refractivity, the relationship between the model and the refractivity. So this forms part of our forward model. It's more complicated than the equation that I showed you on the previous slide. We have a dry term and a moist term. So this is the effective pressure and temperature. This is the bulk of the density. Then there's this is also affected by the partial pressure of water vapor. The electron density, so this is the ionospheric effect that we correct for using the two different frequencies. And then there's the effect of liquid water, in other words, clouds in the field of view. And that's generally assumed to be negligible. So we can remove these terms because we've corrected for this one, and we assume that this one is negligible. However, we still, as I mentioned, have temperature and the partial pressure of water vapor. So yeah, so that is how we forward model radio occultation, and that's the expected impact of radio occultation in our system. I'm going to move on to the other type of GNSS measurement, which is the ground-based GNSS. So in this case, the GNSS satellite signals are received by a sensor on the ground. And the purpose of these sensors on the ground is geodesy. You know, we need to know also plate tectonics, how things are moving over a very, very long period of time. Over long periods of time, atmospheric effects will just cancel themselves out. However, we can see these signals relative to your average. It's the equivalent of something of the path length moving by 2.5 meters in comparison with 20 million meters distance between the ground to the satellite. So the atmospheric delay is for us a signal, whereas it would be a noise for geodesy. So one thing that I don't have on this slide is that if you're not at zenith, we need to convert the image, the signal, to be one that is at zenith, and that's a mapping function which adds a complication to the use of this data. So you've seen this equation before. It's the same as the one used in radio occultation. Except this time we're not looking between two satellites, we're looking between one satellite and the ground, but the fundamental physics is the same. We have, in this case, this term, this change in density with height, is a hydrostatic term, and that accounts for 90% of the total zenith total delay. And the term on the right is a wet term that's variable and related to the integrated water vapor. However, if we have a pressure sensor at the receiver station, we can eliminate the left-hand half of this equation, and our zenith total delay is related to the water vapor pressure against the temperature. And if we know the temperature well, which we're hoping by now because of all these other observations it's getting more accurate, we can work out what the total column water vapor is from these zenith total delay signals. So the errors are assumed to be around 6 to 10 millimeters, and remember that the measurement was around 2 meters, so that's pretty accurate. These measurements do require bias correction, and we do that by building up a model over a period of several months to a year. So they're sensitive to integrated water content and to surface pressure. So those are useful things that we want to know about that are quite complementary to the radio occultation, which is mostly, and the satellite sounding, which is mostly in the upper atmosphere. On the other hand, there's this mapping function to get the zenith total delay back to get the delay from off zenith satellites back to zenith. And that will introduce correlations and errors in the observations, and there's very poor spatial coverage because they're basically only available where these ground networks are. So that basically concludes what I was going to say about satellite data in a numerical weather prediction. I did just want to make a brief comment about ocean DA, and this is really not my area of expertise at all, but I know there are some oceanographers in the room. So I did want to just mention that the main types of observations that are used in ocean data assimilation are altimetry, which provides information on sea surface height for ocean models. This is also a type of radar observation measuring the echo returned from the sea surface, and we basically use a time measurement, the round trip time from the satellite to the sea surface and back again. In this case, we're not interested in very fine scale features, but we're interested in a very broad scale feature. How high is the sea height relative to a reference surface? Then there are sea surface temperature measurements, which can be, this is essentially a level 2 product. It's something that would be derived from microwave or infrared instruments, and as well as ocean models needing sea surface temperatures. The resulting sea surface temperature analyses are also used as input to numerical weather prediction models. And then the other main type of use of satellite data in ocean data assimilation, excuse the typo there, is sea ice. And sea ice fractions and extents are mostly derived from microwave radiometers and radar instruments. So just a quick reference on the principles of satellite altimetry. We have a geoid, which is a gravity potential surface, and a reference ellipsoid. And so we measure the sea surface height relative to the reference, and that's our signal from the altimeter. So the next slide shows the coverage of altimetry data used in the Bureau sea surface model. This is 6 different satellites worth of data, and then a quick data coverage plot for our use of sea surface temperature observations in our ocean models as well. So that concludes my talk. So thank you very much for your time today. And I'm sorry we don't have heaps of time for questions, but hopefully I'll be able to answer some if you have any.
Yeah, thank you. Thank you, Dr. Fiona Smith. Yeah. So is there any questions? Yes.
Hi, can you hear me?
Yes, I can. Thank you.
I have a quick question. So you said that we don't assimilate the temperature and humidity profiles anymore. Instead,
That's
we
correct.
assimilate the brightness temperature. But the cost
Yes.
function that you showed, that has 2 parts. The left-hand side shows the background information, and the right-hand side is the difference between the, basically it's the y minus hx. So if the left-hand side is a geophysical parameter and the right-hand side shows the difference between the brightness temperatures, basically. So how do we do that?
Yeah, so that's where your radiative transfer model comes in. Sorry, I'm just
Is it
whizzing back
like
to try and find it.
retrieval built in the simulated system, or?
So I mean, if you could do a retrieval, you could use this, you could do a 1D var equivalent of this. You could use this exact same system in just one single vertical column and retrieve a profile of temperature and humidity. However, we find that the reason we don't assimilate those retrievals anymore is because they would be dependent on a background profile, and that background profile would have to be some kind of climatology or some NWP information. And then you end up with an observation that's a profile of temperature and humidity, but it's got very complicated errors, and those errors might be incestuous with your NWP model. So we find that the errors are better characterized if we just assimilate the brightness temperatures. But the forward model, this radiative transfer model, is how we convert from model space into observation space. So basically, the radiative transfer model takes in a profile of temperature and humidity and pressure from the model and converts that into a top of atmosphere radiance. Okay. And it's the difference in that modeled radiance and the real radiance that then, through the Jacobian, is mapped back into model space.
Okay. Yeah. Thank you. Thank you.
Yeah. There's a question online I can see.
Yeah, please.
From Prashant. So Prashant says, in the case of all sky assimilation, water vapor channels of the microwave sounder are highly correlated. How do you take care of correlated errors in operational assimilation? So I mentioned the de Rosier method. So we use this technique to derive, basically, that using some assumptions, you can use observation minus background and observation minus analysis. And assuming you know what your background error is, you can then work out what your observation errors are. And basically, those errors are correlated. So we use these diagnostic techniques to tell us what the correlations are. So that gives you correlations between different channels in a single observation. We generally, in data assimilation systems, can't assume correlations between observations in a different location. And that's just a fundamental issue with our current data assimilation systems. So the way we counteract that is to thin these observations out so that they're far enough away that they don't really interact in the assimilation system. I hope that answers that question. Just let me know. You have another question about radar backscatter, assimilation of radar backscatter in the place of wind assimilation. Here we can avoid inverse problems that's performed by retrieval groups. That's indeed true. So I think in a lot of these cases, it's a balance to be struck between having to have a very complicated forward model that is hard for us and maybe not knowing the gradients of that forward model to put into the so in that case the conversion of the backscatter to wind is this empirical model, and so probably we don't know its gradient very well, so it might not be so easy to implement that in an NWP system. I must admit that as you could probably tell from my lecture, my time has been spent working on assimilation of radiances, so I'm not really an expert in backscatter, but you're absolutely right that the errors in the inverse in the process performed by the retrieval groups are something that would go away if we could assimilate the backscatter directly. Okay. There's another question here from Mayank. I hope I pronounced your name correctly. If we have multiple radiosonde observations that provide meteorological parameters like temperature, pressure, and humidity, how can we calculate atmosphere emitted long wave radiation by data assimilation or radiative transfer model? What will be the relevance of this? So yes, OLR tends to be a climate variable. So in climate models, they're very interested in knowing about the outgoing long wave radiation. And certainly satellite data is used for that. And there are radiosonde sites you might know about with specially well calibrated radiosondes called Gruan sites, and so those can be used for those kinds of climate calculations. But outgoing long wave radiation doesn't tend to form an important part of numerical weather prediction, so it's not a field that I know a lot about either. Any other?
Fiona?
Hi, is that Ronnie?
Yeah, actually, nice presentation. You have covered almost all the space-based measurement techniques. Thank you for setting the stage for the next presentation. Thank you very much, and I will hand over to Chandrasekar.
Yeah, good morning. So just one small clarification I should say. Now we know that ocean observations are much less compared with atmospheric observations, especially from satellites. So among all the observations that you listed today, like satellite radiances, then you have the scatterometers, then you have the AMVs, then you have the GNSS. Now, in terms of the actual number of such observations, which is the largest among these? And what is the relative impact of each one of them?
I think that
improving the weather forecast. And is there differences between the weather forecast over tropics and mid latitudes and high latitudes with these observations? Yes.
There certainly is. And I think I'm not going to answer in too much detail because otherwise Indira Rani's talk will be very boring because I will have covered everything that's in it. So if you can wait until this afternoon, I think that will mostly be answered. But just to briefly say that certainly observations from geostationary sounders are very, there's a very large number of those. And obviously hyperspectral instruments have a lot of channels. So there are a lot of observations from a hyperspectral instrument relative to a microwave instrument if you take each channel as a separate observation. In terms of the impact, satellite data are particularly important in the southern hemisphere because we don't have so many conventional observations, and you can really see that. I don't know if I can just maybe quickly share something else. Let me see. I took a slide out, which probably is exactly what you want to see. Let me see if I can find it. Okay, I'll just share again quickly. So on this slide, this plot shows that the lines at this is the accuracy of a day 3 forecast, a day 5 forecast, a day 7 forecast, and a day 10 forecast, and the sort of this darker solid line at the top is the accuracy of the northern hemisphere forecast, and the coloured line at the bottom is the accuracy of the southern hemisphere forecast. So you can see that in the late 90s we started to assimilate satellite observations, and in this case you can see that generally speaking the southern hemisphere forecast at day 3 and day 5 it's particularly obvious. The southern hemisphere forecast has increased in skill much more rapidly than the northern hemisphere forecast, and that's generally attributed to the use of satellite observations. So if you took away the satellite observations, the southern hemisphere forecast would be particularly bad.
Thank you very much for initiating the second week of this workshop. And I think you covered a very, very extensive observations, both satellites, scatterometers, AMVs and GNSS, and also some ocean observations. Yeah, thank you very much. Yeah.
Thank you so much, and I hope that you enjoy the rest of your workshop.